Hi, kiddos. Today we're going to talk about how to determine discontinuities based off limits. So we'll just go quickly through all three discontinuities and then we'll work an example. So I don't know if you remember from Wednesday, you have three kinds of discontinuities. The first one I feel like doing today is a discontinuity. We all know what a jump looks like, but just to be very proper, we're going to draw. So here's a squiggle wiggle that's coming in nicely, and then uh-oh, it jumps here when x equals a. So the looking at a graph and determining what kind of discontinuity is not difficult. And you had a couple homework questions for that. Nobody asked this question. Those are going well. But writing the limit for them is the calculus of this. That's more important to say. So for this jump discontinuity, the reason it's jump discontinuity is that as you approach a, so I'm saying limit, approach, from the left of our function, which I'm going to call f, and then as you approach a from the right, and that's a limit again because I'm saying approach, and I'll call it f, you're not getting the same value. That makes it a discontinuity. That's a jump discontinuity. The second kind of discontinuity, we'll do a whole. Remember that it's also called a removable discontinuity. So this could look like a lot of different things, but I'm going to squiggle wiggle on over here, have a hole, and then squiggle wiggle out. I'll call this A again, and let me close the function value. So we have three conditions for continuity, and we talked about this on Wednesday. The first condition is that your function has to exist at A, and this one does exist. The problem here is that as I approach A from the left, and as I approach A from the right, I get the same thing. So the problem with this one, so the limit of f of x as x approaches a also exists. The problem with the whole is that third condition. So the problem here would be that f of a, your function value, doesn't equal your limit. So your limit exists because the left and right match, and that's all it takes. But it's not the same as your function value because you got a dot floating in space. Again, another one that's really easy to read just from a picture. But I need you to be able to read it from a limit too. So if I gave you this information and I just said to you, what kind of discontinuity does this define? You would need to be able to tell me that that means it's a removable. All right, last one would be a infinite discontinuity. Here's my paper. There it goes. So an infinite discontinuity, also lovingly called an asymptote. I guess I should be more specific, a vertical asymptote. All right, we all know what vertical asymptotes look like, but I'm going to draw a picture again. I'm going to swoopy that one up. Here's my asymptote. How about A? And I'll swoop from this side too. This one can go wrong a couple different ways. Your asymptote can go wrong a couple different ways, your discontinuity. But the one I need you to know is that when I take the limit as x approaches A from either side, left or right, of my function, I get an infinity. It doesn't matter that one side's positive and one side's negative. And I know and you know that that means the limit doesn't exist, but it needs to not exist because it goes to infinities, and that's what makes it a vertical asymptote. I hope that's not new information for you. Don't think it is. Because I want to be thorough today, I'm also going to talk about a horizontal asymptote. Horizontal asymptotes are not discontinuities. I don't have to pick up my pencil when I'm drawing a squiggle wiggle that has a horizontal asymptote. And these are going to exist at y values, so I need to put a up there. So I have my squiggle wiggle coming in hot and then going forever that way. I didn't have to pick up my pencil to draw it, so this is not a discontinuity. I just want you to see what the limit looks like. This time, because it's still an infinite limit, this time the limit as x goes to infinity of your function equals a value. That's what makes it a horizontal asymptote. And I'm going to put a plus or minus because it can go to either infinity. That's kind of it. Like those are your three options for discontinuities, and then a little added bonus about horizontal asymptotes. What I want to do now is give you a function, and let's talk about all of the discontinuities. So for a Hemplo, here's a function. It looks like this. It's just a boring old rational function. I know that you took pre-calculus. I've also taken pre-calculus. And I know that when you took pre-calculus, you were able to factor cancel and just immediately say that things were asymptotes or holes based off the algebra that you did. I know that. I'm very proud of you. I'm very happy for you. But now you're in calculus and you have to justify discontinuities with calculus. So if you are ready to dive right into this and say, looky how smart I am, this factors as x plus 2, x minus 4, I would say, yes, my darlings, I agree with you. And then what you really want to do is you want to go cancel, cancel, and plan. I need you to slow your roll a little bit. If you need to pick, these are your uh-ohs. You got to pick your uh-ohs before you do any canceling. So I know enough about functions and I know enough about math to know I can never divide by 0, which means I have two uh-ohs to consider. I need to x is negative 2, because that's going to give me a discontinuity of some sort. And I need to pick x is 4, because that's going to give me a discontinuity of some sort. All right. After that, after you've picked your points, then you can reduce your function if it reduces. This one does. You're welcome. So x plus 2 reduces. This is I'm going to use in my calculus, but I had to pick my values first. All right, so there are 3 conditions for continuity. There are 3. There are always 3. You already know that your function value is undefined, doesn't exist. That's how you picked that as an uh-oh point in the first place. So that's not helpful to you. Your second condition for continuity has to be the limit. So we're going to go take the limit as x approaches negative 2 of 1 over x minus 4. And these have got to be quick. If they're not quick, you're probably doing too much. Because if I just plug in, I got negative 1/6. So here's what you know. The limit exists because I got negative 1/6, but the function value does not exist at that point. What kind of discontinuity is that? So come over here and say, therefore, removable discontinuity at, I'm just going to give the x value, but if you remember from pre-calculus, you now know exactly that there is a hole, negative 2 comma negative 1/6. Okay, because remember this is your input, this is your output. So there's your x and your y. So the function value didn't exist, but the limit from both sides of negative 2, we're going to give that same limit of negative 1/6. So the limit agrees, the limit matches, the limit exists, but it doesn't match your function value. And that's how we define a hole, a removable. All right, let's come over here. If I do f of 4, the same thing's going to happen. I know this feels like unnecessary work, but I want to walk through all your conditions. So I know I have a discontinuity now. I just don't know what kind. This time, when I go to take my limits, I have to come at 4 from both sides. Here's why. If I just start here and I plug in a 4 without thinking about it as a left or a right, I'm going to plug in and I'm going to get 1 over 0. But I need to know what kind of 0 so that I can know what side of infinity I'm dealing with. So it's real easy. I'm not erasing. I'm just going to go say, oh, let me do left real fast. All right, left of 4 is a number that's a little bit less than 4. A number a little bit less than 4 minus an actual 4 is going to give me a negative 0. So a positive divided by a negative is a negative infinity. I'll do the same thing on the other side of 4, the same function. So this time I plug in, I got 1 on top, I got 0 on bottom, but bigger than 4 minus actual 4 is going to give me a positive 0, and this one's a positive infinity. I know, you know, we know these are not the same thing, and so we can say the limit does not exist, and that's absolutely correct. It's just not helpful right now. What I need to know here the point of this is that I can come down and say, therefore, we're going to have a vertical asymptote, or you can say an infinite discontinuity. AP is pretty lenient with this language. They'll use either. So as long as you know that they're both fine. A vertical asymptote at, you can't just say 4, you have to say x equals 4. It's a vertical line, so it's an x value. And now you have just shown me for this beautiful function we started with, it's got 2 points, 2 places of discontinuity, one at -2 and one at 4. You have used limits to prove to me the kinds of discontinuities. Okay, here's what I'm going to say it again. I've already said it once. I'm going to caution you again. I know you took pre-calculus. Congratulations. But if you come in here, you factor these, you say cancel, therefore whole, I'm not going to give you any points for that. If you don't show me limits when you're talking about continuities or discontinuities, I will give you 0 credit because I am a calculus teacher, and that's the way you prove discontinuities. All right. This is the last lesson for this unit. So this will get you through Friday. And then on Monday, you have a Desmos card sort, a couple of them to practice. And what you're going to end up practicing is matching a graph with a function, with limits, with words. So you're going to kind of tie everything together on Monday. And then we'll worry about a continuity quiz coming up. Text me with questions.